Section 3.7, Limiting and Excess Reactants. This section will build upon the stoichiometry concepts we discussed in Section 3.6. Let's start with some basic terms. The limiting reactant, which is abbreviated LR, determines how much product can be made in a chemical reaction. This reactant will also run out first, and once it's gone, the reaction will stop. The excess reactant, abbreviated XS, instead of ER because ER is emergency room, this is the chemical where more than enough is present and some will remain after the reaction stops. Sometimes kids can understand limiting and excess reactants if you look at it from a recipe or a food standpoint. Let's say the reaction, so to speak, we're going to study is making grilled cheese sandwiches. And you go home and in your kitchen you find 12 slices of bread and 8 slices of cheese. Assuming that a grilled cheese sandwich is made from 2 slices of bread and 1 slice of cheese, let's think about how many sandwiches we should be able to make. If you consider only the bread, and you have 12 slices, then you'd think, well, I should be able to make 6 sandwiches from that. If you consider only the cheese, and you have 8 slices, you might think you can make 8 sandwiches. But looking at those two materials together, we know that truly you could only make 6 sandwiches because then your bread will be gone and you'll have to stop making sandwiches. So in that example, the limiting reactant would be the bread, because it limits us to making only 6 sandwiches and we'll run out of that material first. The cheese would be considered the excess reactant because I have more than enough cheese to make those 6 sandwiches and I'll have 2 slices of cheese left when my sandwich making is done. As we try to understand these terms in the chemistry sense rather than a food example, we want to try to identify this type of calculation in comparison to the other things we've been working on in Chapter 3. Many students realize that there are so many types of calculations to keep straight. We've worked on molar masses and percent composition, empirical and molecular formulas, and yesterday we introduced stoichiometry. One thing that sets apart these types of calculations from the ones we've done previously. In a limiting and excess reactant problem, there will always be 2 given numbers. So if you think back to the stoichiometry that we worked on yesterday, the problem may have been worded, you have 40 grams of hydrogen. How many grams of water could be produced starting from this amount? And there's one given number in that problem. The problems we will see today, there are 2 given numbers, or 2 A's in terms of our stoichiometry diagram. So that's one thing that sets these types of problems apart from others. Let's take a look at the steps used to determine the limiting reactant. Step 1. Select one of the given numbers and use stoichiometry to calculate amount of product. Remember, you'll be given 2 given numbers in the problem, so just select one. I tend to just pick the first one in the problem. Step 2. Repeat with the other given number. So essentially you'll be doing your stoichiometry twice. Once with one of the given pieces of information and a second time with the other piece of given information. Again, go back to that grilled cheese example. If you think about the 12 slices of bread, looking at only that, I would think I could make 6 sandwiches. But looking at the 8 slices of cheese, I would think that I could make 8. Now I have 2 answers, 6 sandwiches or 8 sandwiches. And we know that 6 is really the correct answer. So in this process as well, you have to look at the 2 answers you've determined. So you need to compare those answers. And I always encourage students to right away cross out that bigger number. It is not an amount of product that we can actually make, and it's not useful in our problem at this point, and so we want to eliminate it. We also should box the smaller number because that's the amount of product that we actually can make. And the term for that's used in chemistry for that amount is the theoretical yield. The theoretical yield is the maximum amount of product that can be formed, assuming that everything goes really perfectly. Back to our grilled cheese example, you should be able to make 6 sandwiches. But if you were getting your items ready to, your grilled cheese materials ready to make, and you dropped a piece of bread and cheese on the floor and your dog came by and ate it before you could grab it, well, then what should have ended up as being 6 sandwiches is actually going to end up being less than that. So that term theoretical yield, think of the phrase in theory, that's how much you should be able to make, but keep in mind that in actuality you might not end up with that much. Since there's so many calculations going on, and kids sometimes tell me they have a hard time keeping everything straight, I always encourage them to label what I call the big 5. And in that labeling process, you'll end up putting an X through the bigger answer, as I mentioned earlier, a box around the smaller answer, and then you want to continue to label the limiting reactant, the excess reactant, and the theoretical yield. And we will look at an example of how to do that. Often when you do limiting and excess reactant problems, they also ask you for something called percent yield. And percent yield is a way for chemists to know, how did I do? How much chemical did I produce compared to how much I should have? And the setup for percent yield is actual over theoretical times 100. And another way to think of it is, how much did I actually produce over how much should I have been able to produce times 100. And the closer to 100% yield you obtain, the better. Generally in lab, anything over 90% would be considered very good. However, if you calculate your percent yield and you get over 100%, then you should double check your calculations because there's probably an error at some point. Let's take a look at some examples. Consider the following reaction. 3 hydrochloric acid plus aluminum hydroxide yields 3 water and aluminum chloride. Letter A says, if you were given 45 grams of HCl and 15 grams of aluminum hydroxide, how many grams of water can be produced? And one thing to notice, as we discussed, there are 2 given pieces of information, 2 numbers or 2 A's from your stoichiometry diagram. So when you see these 2 numbers, you may want to just label them as A1 and A2. They will be the 2 numbers that we start with as we start doing our calculations using stoichiometry. Also, I notice it says how many grams of water can be produced. This is my B. This is what I'm looking for. So pick one of the given numbers. I'm going to start with the 45 grams of HCl because it's listed first, but it truly doesn't matter. We want to go on your stoichiometry diagram from grams of A to grams of B. So we start by changing grams to moles. If you consult your periodic table, you'll find that 1 mole of HCl is 36.4609 grams. And I obtained that by adding together 1.0079 and 35.453, the atomic masses of those 2 elements on the periodic table. Next, we need our mole-to-mole ratio. We are trying to solve for grams of water produced. So I look at the coefficient for water in the equation, and it is a 3. So I would put 3 moles of water on the top. Remember, it's always moles of B over moles of A, moles of what you're trying to find over moles of what you've been given. We started with HCl in this problem, and the coefficient on HCl also happens to be 3. So our mole-to-mole ratio is 3 to 3. Our last step is to convert moles to grams. And for every 1 mole of water, if you add up its molecular weight on the periodic table, 2 H's plus 1 O, you would get 18.0152 grams. If you go ahead and crunch those numbers, this should give us an answer of 22.2 grams of water. And we'll revisit that in a second when we compare our answers. The other given number, A2, is 15 grams of aluminum hydroxide. Keep in mind we still want to solve for grams of water, so it'll be another grams of A to grams of B calculation. For aluminum hydroxide, we need to change it to moles, so if you add up aluminum, 3 O's, and 3 H's, you should obtain a molar mass of 78.0034 grams. This time around, our mole-to-mole ratio is not going to be 3 to 3. The water on the top in the numerator will still have a 3 because of its coefficient, but aluminum hydroxide, there's only 1 mole. So instead of 3 to 3, our mole-to-mole ratio will be 3 to 1. So 3 moles of water for every 1 mole of aluminum hydroxide. The last step is to again convert to grams. And the molar mass of water is 18.0152 grams per mole. And after crunching numbers, we obtain an answer of 10.4 grams. At this point, we've done all our calculating, and we need to kind of take a step back and look at our answers. When we label the big 5, these are the things you should label as you're looking at your calculations. We want to cross out the bigger answer. So looking, I have 22.2 grams of water and 10.4 grams of water. So I'm going to cross out the bigger one because that numerical answer is never a possible amount of product to form. I put a box around the smaller answer and label it as theoretical yield, TY. So I've done 3 of the 5 things in the big 5. We also have to determine the limiting and excess reactant. The limiting reactant is the one that produces the smaller amount, the one that limits or determines how much product can be formed. So here's our 10.4 grams. Now keep in mind 10.4 grams, that's grams of water. And water is a product. It's on the right side of the equation. So we should not label anything about limiting and excess over on this right-hand side because those are both products. If we go back to the left, where the HCl and aluminum hydroxide are, those are our reactants. So one of them will be the limiting reactant, and one of them will be the excess reactant. Again, the starting material that limits or determines how much product can be made is the limiting reactant, and the reactant that will be left over at the end is called the excess reactant. Now some students have told me that since you draw this big X through the bigger answer, if you just extend back to the beginning of that line, that will be your excess reactant. So if we answer the other questions with question 1. Letter B, well first of all for letter A, the question originally was how many grams of water can be produced. We've already answered that, 10.4 grams. B, what is this amount of product called? It is called theoretical yield. Which reactant is limiting and which is excess? We've identified those. Our limiting reactant is aluminum hydroxide, and our excess reactant is hydrochloric acid. Letter D, if we carried out this reaction in the lab and actually obtained 8 grams, what is the percent yield for this reaction? Percent yield is calculated by dividing actual yield, what you obtained, over theoretical yield, what you were supposed to be able to produce, times 100. So in this problem, it says our actual yield is 8 grams, and we should have been able to produce 10.4 grams, times 100 gives us a percent yield of 77%, which is okay, it's decent, but ideally we would want a percent yield that's a little bit higher. At this point, I'd encourage you to take a look at the second set of calculations for practice, and feel free to pause the video while you're working on those, and then we'll take a look at the answers once you finish. In this example, acetylene, C2H2, will burn in the presence of oxygen, and they've provided a balanced equation for us. 2 moles of acetylene plus 5 moles of oxygen yields 4 moles of CO2 and 2 moles of water. Letter A. If you are given 124.8 grams of acetylene and 473.6 grams of oxygen, what is the theoretical yield of carbon dioxide in grams? To help organize our thinking, this first number that I see, 124.8 grams of acetylene, that's going to be my A1, my first given number. 473.6 grams of oxygen, that's my other given number, so I'm going to label that A2. And I know I'm looking for the theoretical yield of carbon dioxide in grams, so that is my letter B, my unknown. So if we follow the same process outlined in the notes, we would start with 124.8 grams of acetylene, C2H2. We would change it to moles. Using your periodic table, 1 mole of C2H2 has a molar mass of 26.0378 grams. We're solving for carbon dioxide. Very important that you take a look at the mole-to-mole ratios. Carbon dioxide has a coefficient of 4, and acetylene has a coefficient of 2. So our mole-to-mole ratio is 4 moles of CO2 for every 2 moles of acetylene, C2H2. Our last step, since they ask for the yield in grams, is to convert moles to grams. And for every 1 mole of carbon dioxide, it has a molar mass of 44.0098 grams. Calculating, this should give us an answer of 421.9 grams of C2H2 acetylene. Starting from our other given number, 473.6 grams of oxygen, we want to again begin by changing grams to moles. So 1 mole of oxygen, if you add up O2 on the periodic table, 31.9988 grams. The ratio of carbon dioxide to oxygen is 4 to 2, so we're still trying to determine the amount of carbon dioxide, but this time our given chemical was oxygen, so 4 to 5 ratio. And the last step is to change moles to grams. Now, one of the convenient things about this method is that the last conversion factor in the first and the second calculation are always the same. So if you've added up the molar mass for CO2, 44.0098, you should use that same number in the second part of the calculation. This time around, I obtain an answer of 521.1 grams of, I labeled this one incorrectly previously. This should be CO2. 521.1 grams of CO2. Again, we want to take a minute and label our big 5. We cross out our bigger answer, we box the smaller answer, and label it theoretical yield. We go back to the left. The one with the X, X at the end of the answer, is our excess reactant. The other one is the limiting reactant. And by taking the time to label all those pieces of information, we should be able to answer the other questions fairly easily. Because A was asking us, what's the theoretical yield of carbon dioxide in grams? We've already answered that here, 421.9 grams. B, which reactant is limiting? Acetylene, C2H2. If 378.4 grams are actually produced, what is the percent yield for this reaction? Remember, percent yield is calculated actual over theoretical times 100. So if we actually produce 378.4 grams, and we were supposed to be able to produce 421.9 grams, that gives us a percent yield of 89.69% to 4 sig figs, because both my numbers had 4 sig figs. So an improved percent yield over the situation in problem number 1. Now, one last question that is sometimes asked when you're completing stoichiometry is how many grams of excess reactant remain after the reaction. And if you think about it, if you work in a chemical industry or manufacturing plant, you don't want a lot of excess reactant to remain because that will reduce your profits. You want to minimize the amount of excess material that's left over because otherwise it's just wasted and will be costing your company money. So let's take a look at our last slide and see what steps are used to determine the amount of excess that remains after the reaction, and then we will finish up this letter D. Calculating amount of excess reactant left over. If you haven't done so already, the first step would be to determine the limiting and excess reactant. Step 2, use stoichiometry to determine the amount of excess reactant used or consumed. We want to know how much in the process of the reaction is actually used up, and once we have that amount determined, we can subtract it from the original amount. Now, when you're using this stoichiometry, the key is to use your given information as the limiting reactant. So A is going to be the limiting reactant. B, or the unknown, is going to be whatever the excess reactant is. And once you've determined how much of that excess reactant is consumed or used up in the reaction, the last step is just to subtract it from the original amount. So let's take a look at part D on that same problem we were just working on. Letter D says how many grams of excess reactant remain after the reaction. As the last slide discussed, when you're trying to find the amount left over, the key is that you set up A, or use A as your limiting reactant, and your B should be the excess reactant. So A is going to have to be acetylene, because that was our limiting reactant in the problem. B is going to have to be oxygen, which was our excess reactant. So we're going to start from this given amount of limiting reactant, 124.8 grams of acetylene. We will change grams to moles, and the molar mass from acetylene, we used it in part A, is 26.0378 grams. This time we're solving for the excess reactant, which is oxygen. And if I look at my balanced equation, the ratio of oxygen to acetylene is 5:2. So that should be the coefficients we use in our mole-to-mole ratio. So 5 moles of oxygen for every 2 moles of acetylene. And the last step would be to change it to grams. 1 mole of oxygen, 31.9988 grams. The number we come up with is 383.4 grams of oxygen. Now, many students think that is the answer. That is the amount of oxygen that is used in the problem. So, not really our answer yet, just the amount that's used. If you look at the original problem, we were given 473.6 grams of oxygen. So I started with 473.6 grams. I subtract the amount that's used up in the process, and when I subtract, I should get 90.2 grams of oxygen left over, or in excess. So if this was a process we were using in class, we'd want to make sure to, or in an industry setting, let's say, if we were purchasing oxygen to do this reaction, we'd probably want to start with a little bit less of it in our reaction, because at the end of this reaction, 90.2 grams of oxygen would be left over. And if I'm paying for that oxygen, then clearly that would be a waste of money for my company. That brings us to the end of section 3.7. Please see me if you have questions.